We want to now begin a discussion of energy with regards to the entire atom structure, because energy does have a lot to do with the behavior of an atom. If we just define energy, you will see lots of different definitions for energy. Capacity to cause change is kind of a very popular definition that you see. Sometimes we see the ability to do work. That's another very common definition here. There are different types of energy. We have basically potential and then what we also call kinetic. And in this particular chapter, we're really going to be focusing on the potential energy. When we talk about potential energy, this is energy that matter possesses because of its location or its structure. If you think about any matter, whether it is living or non-living, that particular matter is going to have a place where it is located at, so it will have a location, and it is going to have some kind of a structure or shape to it. So if we just talk about your textbook, for example, that textbook may be sitting on your desk. Okay, that is where it's located at. It does have a shape to it, so it's like a box, rectangular in shape. So it does have an amount of potential energy within it because of its location, because of its structure. If it was in another location, or if it had a different shape to it, then it would have a different amount of potential energy. Now, if we consider that textbook a little more, if it's sitting on your bench or your desk right now, if you were to slide it off of the desk, obviously it would fall to the floor. Okay, so when it's sitting on the floor, it's going to have a different amount of potential energy because now it's not in the same location as it was before. Notice that if the desk is not holding it up, it wants to go to the floor. Now we know that there is some gravity involved in that, and we're not going to get into a discussion of gravity, but notice that it goes to the floor. Now, can it get back up on the desk? If you bend over and pick it up, it can get back on the desk. But notice that you're going to have to do some work to get it back up to that desk if you want to. So matter, whether we're talking about your textbook or some other matter, it has a natural tendency to move to the lowest possible state of potential energy. So when we have something at its lowest possible state of potential energy, that will be where it is most stable. Okay, so that's where things want to be. That's where your textbook wants to be, on the floor, if we're not preventing it from going to the floor. So if the desk is holding it up, or if you're holding it in your hands and you're holding it up, then it's going to be further in the air. But if you don't hold it up and prevent it from going to the floor, it will go to the floor. So we're going to take that same idea and we're going to apply it to the structure of an atom. And basically, the further in the air that you move that textbook, the more unstable it would be. So it's very stable when it's sitting on the floor, and then as we move it up, kind of has farther that it could fall, and then it would not be as stable. So we talk about the atom structure and this same kind of idea. In this picture, at the top, you've got kind of the ball bouncing down the stairs, and that's similar to the textbook example. Because if you don't prevent it, that ball will basically roll to the floor or the very bottom of the stairs. Okay, that would be where it's most stable. Okay, so this ball down here, it's most stable, which means that's where it wants to go, which we could also say is where it has low potential energy. They'll call it PE. Here, it's going to be less stable, and it will actually have more potential energy. Okay, so at the top, it would be the least stable, and that would be where it has the most potential energy. Okay, so notice that as we get less stable, we have more potential energy. So there is this correlation between stability and the amount of potential energy that matter is going to have. Where it's very stable and comfortable will be where it has low potential energy, and that's really where the matter would ideally like to be stable. Now if we look at the second picture here, which is the picture of an atom, in this particular picture we see that a quarter of an atom really. We've got the nucleus here, which is going to have the protons and the neutrons there. But keep in mind the protons have a positive charge, the neutrons have a neutral charge, so overall that nucleus is going to have some kind of a positive charge to it. The electrons, we said, were going to be located somewhere further out from the nucleus. These places where they're actually located at are what we call energy levels. Okay, these energy levels, these are distances from the nucleus where the electrons will actually reside at. The electrons have a negative charge to them. So if you have an electron, if we just consider that maybe we have an electron sitting here on this very first ring here, that electron has a negative charge and opposite charges attract each other. So similar to the way that the book is attracted to the floor because of gravity, that electron is attracted to the nucleus because it's opposite charges there. So if we have an electron that is fairly close to the nucleus, like on this first level or this first ring, these are going to have less potential energy and they will be more stable. If we have an electron that is located further out, say on the second ring, these are going to have more potential energy and they are going to be less stable. And basically the further out we move to the third level, the fourth level, and so on, we're going to get electrons that have more potential energy. They have further that they can basically fall to that positive nucleus, and they're going to be lower in their stability. The electrons are going to be located at set distances from the nucleus. They can't reside just kind of randomly anywhere they want at any particular distance from the nucleus. So they will be at some set distance, which does correlate to what we're calling the energy levels or the energy shells here. And the amount of potential energy that an electron has does relate to which shell it's actually sitting in. Now, just like it's possible for you to get that textbook and pick it up off the floor, it is possible to move an electron from one level to, say, another level. So if we wanted to move this particular electron out to, say, this further ring, like picking the textbook up off the floor, if we want to do that, we're going to have some energy actually put in to make this happen. So if you want to get the textbook up, you have to bend over and you have to pick it up and move it up to the desk. If we want the electron to move further out, we've got to have some energy to actually move it further out. This does happen. We will see examples of this happening when we get to chapter 10. We'll see quite a bit of it. Chapter 10 is about photosynthesis. And with photosynthesis, light energy comes into a plant and it's going to basically energize electrons. And when we energize those electrons, we're going to see them move to a higher energy level, and they are going to become more unstable. Because again, the further out we're getting, the more potential energy that we're getting, the more unstable that electron is going to be. We want to make sure that we understand the correlation between the amount of energy, potential energy, that an electron has, and the distance that it is located from the nucleus. Now, if we look at this slide here, we see all of these diagrams showing the electrons sitting on their electron shells or their energy shells around kind of a generic nucleus. Now, if we look here at the first one, we have hydrogen. Hydrogen has an atomic number of 1. And if we assume that this is going to be a neutral hydrogen, then it is also going to have 1 electron. Okay, so we see that on this shell we have 1 little yellow dot located there. If we go down to carbon, for example, carbon has an atomic number of 6. If it's a neutral carbon, then we're also going to have 6 electrons there. So we see 6 little dots arranged around the generic nucleus. These pictures that we're looking at are what we would call electron configurations. Electron configurations are basically pictures showing the electrons. And in addition to showing the electrons, they're showing exactly what shells or which energy levels they are located at within. Now we're going to learn how to draw these electron configurations. And so if we're drawing the electron configurations, we need to understand a few rules that are involved. Okay, so one of the first things with the electron configurations is that we need to know how many electrons are going to be located in the shells. The first shell, that would be the innermost shell. So by innermost shell, we're talking about the shell that's closest to the nucleus. So that would also be the lowest energy shell. That first shell is going to hold a maximum of 2 electrons. We will never be able to put more than 2 electrons into that first shell. Now that first shell we're also going to fill up first. Okay, and if we fill up that first shell and we still have additional electrons, then we will move on to the second shell. So when we look at the second shell is going to hold a maximum of 8 electrons. And if we fill up the second shell, then we would move on to the third shell, and so on. Now you can certainly go into a lot of detail on electron configurations, and I'm sure when you do get to chemistry courses, you will go into more detail than what we're going to cover right here. But we're going to learn how to draw very basic electron configurations so that we can understand bonds that atoms are going to want to make. So if we look at an example here, we're going to look at nitrogen. Nitrogen, if you find it on your periodic table, it does have an atomic number of 7. So if we are dealing with a neutral nitrogen, we are going to have 7 electrons. If you're going to draw electron configurations, really the very first step is to figure out how many electrons you're actually dealing with. Okay, if you don't know how many electrons you have to arrange on your picture, you're not going to be able to come up with the picture. Okay, so if we come up with 7 electrons, we're not really interested in the nucleus, so we don't want to draw that in a lot of detail. Just put something there that's going to kind of indicate your nucleus. So this could be a circle, a dot, whatever. And then we're ready to begin drawing the electron configurations. Now, as we said, we want to draw the first shell, or put the electrons in there first. So I'm going to draw my first ring here. This would indicate my first shell, which really is just a distance from the nucleus. And within this first shell, I'm going to put the electrons, 2 of them, basically right next to each other. You can draw these as dots, you can draw them as X's, however you want to indicate them. But when we do fill that first shell, notice that we want to put them next to each other. In other words, we are making a pair. Okay, so by a pair, we're basically sticking them right next to each other. Now once we put those 2 on there, we have filled up the first shell, and we had 7 total electrons we needed to put on this diagram. So that means that we do, in this case, need to draw a second shell on there because we need to start putting the rest of them on. So I'm going to go ahead and draw the second shell. And when I have that second shell, I want to think of it as having 4 different positions to it. We've got basically a top, we've got a bottom, and we've got a left and a right here. Okay, so we've got 4 different positions. As we go around and start filling the second shell with whatever remaining electrons we have, we want to put 1 electron in each one of those 4 positions before we start adding a second electron in each one of those positions. So you can start at any one of the 4 positions you want. I tend to start at the top and work my way around. So we've got 2 electrons and we need to go up to 7. So this would be electron number 3, 4, 5, 6, and then my 7th electron I'm going to put right back up here in my top position. So when we look at that outer shell, notice that you've got 3 electrons that are all by themselves. So those are what we would call unpaired electrons. And you've got a pair of electrons up at the top. It is very important, it's critical really, that you use the 4 positions on the circle, because it will become very important that to get the right number of unpaired electrons versus paired up electrons. We most definitely do not want to just go around and equally space the electrons on the outer shell. In addition to that, you want to make sure that we do pair up the electrons on the inner shell as well. That does vary a little bit from textbook to textbook, but with your textbook it does take that first shell and it does pair the electrons up. So that is certainly the way that we want to approach that. If we look at another example, if we had, for instance, we'll do carbon. Carbon has an atomic number of 6. So here we have 6 electrons. We draw the nucleus. We draw the first shell. We put our electrons in the first shell. We get 2 of them. Then we have another 4 electrons that we need to put on there. So we draw the second shell. We hit the 4 positions before we start doubling anything up. So there's 4, 5, and 6. Notice in this particular case, we only get 1 electron in each one of the positions on the outer shell. Now that outer shell does fill up, that second shell, it fills up with 8 electrons maximum, so that would indicate 2 electrons in each one of the 4 positions. And if we had more electrons still, then we would need to draw a third shell, and we have shells beyond that as well. So there's actually 7 different shells. We will not go beyond the third shell actually having 8 electrons in it. Okay, but do be aware that there certainly can be bigger atoms than that. If we look at the periodic table, just again, notice that there is a lot of organization with regard to the periodic table. So the very first row, everything has 1 shell and only 1 shell. The second row, everything has 2 shells. The third row, everything has 3 shells, and so on. So in addition to the fact that the atomic numbers go up as you go across the rows, the number of shells goes up as you move down the periodic table. And as you go down the periodic table, your elements and atoms are certainly getting larger. Now if we talk about valence electrons are nothing more than the electrons that happen to be in the outermost valence shell, whatever that shell happens to be. So notice for the first row, the valence shell would be the first shell. For the second row, the valence shell would happen to be the second shell. The third row is the third shell. Okay, so notice that does depend on the atom that we're actually looking at. But the valence electrons, they're going to be very important because these will be the ones that determine the chemical behavior of the atom. Basically how it wants to behave when it interacts with other atoms. Keep in mind that the valence electrons are on the very outside of an atom. So if you have an atom that's going to be bumping into something else, it's going to be these outer electrons that would be the ones doing the bumping or doing the actual interaction. So if we look back at our nitrogen example here, you've got the diagram in front of you. Notice that nitrogen has a total number of electrons, and that would be 7. Okay, because it's neutral, so it does have 7 electrons. The number of valence electrons, though, that will be 5. Okay, because for valence electrons, we're only counting up the ones that happen to be on the outside ring, which in this case is 5. So we don't want to count those inner 2 electrons in that number at all. Okay, so the valence electrons, if you do look down the columns of the periodic table, notice as well that not only as we go down the rows are we ending up with an extra shell on there, but as you go down a column, you've got the same number of valence electrons for those. So for instance, nitrogen and phosphorus both have 5 valence electrons. Carbon and silicon have 4 valence electrons, and so on. And that's going to mean that within a column, they're going to behave very similar to each other because it is the valence electrons that determine an atom's behavior. Now, we said that when atoms interact with each other, they're going to be doing so to complete their valence shells. What that means is that they really want to fill up that valence shell, max it out. We said that for the first shell, that would be a maximum of 2 electrons. For the second shell, it's going to be 8 electrons. And for the third shell, we're going to think about 8 electrons there as well. So in order to complete or fill up the valence shell, the unpaired electrons that we have are basically going to want to find a pair. Okay, so they want to find a partner to sit right next to them in the circle, and if they do, then we would have a full outer shell. So this is where our bonding starts to come into play. So if we introduce some types of bonds, covalent bonds will be our first type of bond. These are going to be very common bonds, and they're ones that we're going to see kind of all semester long. Covalent bonds are defined as bonds that occur when we have a shared pair of valence electrons between two atoms. So it's really characterized by this sharing word and its valence electrons. Okay, so we're sharing electrons between two atoms. No atom is going to gain extra electrons, nobody's going to lose electrons, which means we're not going to have any kind of charge change. So if we start with neutral atoms, we'll end with neutral atoms. So I'll draw this as best I can here, but it may get a little sloppy. If we draw, for instance, a carbon, and I'm going to write a C in the middle of the nucleus just so we can remember that this is our carbon here. Carbon has an atomic number of 6, which means that basically we have 6 electrons if we're dealing with a neutral carbon, which is what I'm going to draw right here. So we've got our neutral carbon, and if we draw the electron configuration, this will be my first shell. Okay, and on my first shell I'm going to put 2, draw them as little x's, and on my second shell I'm going to have 1, 2, 3, 4. Okay, let me kind of shade this in so we don't think that that's a shell in there. Alright, so notice that I've got a total of 6 electrons, and I've got 4 unpaired electrons on that outer ring. For carbon to be really stable, it would like to fill up the outer ring, or fill up the outer shell, basically have 8 electrons in there. So it's actually 4 electrons short. Another way to look at it is that each unpaired electron would like to have another electron sitting right next to it. So they would like to be paired up. If we look at hydrogen, hydrogen has an atomic number of 1. This means that a neutral hydrogen has 1 electron. Okay, so if we draw hydrogen, there's its first shell, and I'm going to put its 1 electron right there. Okay, so hydrogen would like to fill up its outer shell, which would be 2 electrons since it happens to be the first shell. So notice if this hydrogen basically migrated over here, and then it shared basically, if I draw it right here, we have our hydrogen, and it's got its 1 electron. So if it shared its electron with the carbon, and the carbon shared its electron here with the hydrogen, that actually would fill up the outer shell for the hydrogen, because for the hydrogen it just needs 2 electrons to fill up the outer shell. If we had another hydrogen come down here and share an electron, we've made that hydrogen very stable and happy. If we put another one over here, got the same situation, and then I'm going to put another one up here. Okay, looks kind of sloppy, but hopefully what we can see here is that we've taken 4 hydrogens. Each one of those hydrogens shared their 1 electron, shown as a dot here, with the carbon, and the carbon shared its electrons with each one of those 4 hydrogens, and when that happened, we've now filled up all of the hydrogens' outer shells, and we have actually filled up the outer shell of the carbon as well, because the carbon now has 8 electrons in that second shell, which does max out that second shell. That's what we're doing with a covalent bond. So with a covalent bond, you've got atoms that are actually sharing electrons with each other. When they share electrons with each other, that's going to fill up the outer shell of each one of them. Notice that nobody's losing electrons and nobody's gaining electrons, which means that we're not altering charges here at all. Okay, so we're still maintaining a neutral atom. It is, however, a sharing between atoms, so it is a physical link because they're each kind of holding on to a piece of the other one. Now, once we start to connect atoms together with covalent bonds, this is what we call a molecule. Okay, so what I just drew for you would be called a molecule. If we look at it a much simpler way, you've probably all seen at some point in your life molecules drawn like this. Okay, so in this picture, we've got a carbon in the center and it is surrounded by 4 hydrogens, which is exactly what we just drew. What these little dashed lines are representing is this is representing the pair of shared electrons. Okay, so we could draw them in here if we wanted. I'll draw one as a dot, one as an X, indicating that one was from carbon, one was from hydrogen here. Okay, so each line is representing one pair of shared electrons. That there is a molecule because we have shared electrons between 2 atoms. Now we can have one pair of shared electrons between 2 atoms, which in this example we have basically 4 what we would call single bonds or single covalent bonds. So between the carbon and each hydrogen there is only 2 total or 1 pair of electrons. We can also have what we call double bonds. And if we're talking about double bonds, you would actually have 2 pairs of shared electrons. So if we look at an example of a double bond, if you look at the bottom here with the double bond, first off, if you look at those oxygen pictures, the electron configurations are not drawn properly. Okay, so this picture came from a different textbook. One of the reasons I put it in here is because it's not drawn properly, so when you first glance at those oxygens, it's really difficult to see how many unpaired electrons they're going to have. And if you can automatically see how many unpaired electrons you have, you can predict how many bonds the atom wants to make, because every unpaired electron wants to get a pair next to it. So if I just quickly draw the oxygen electron configuration up here, the first shell has 2, and then the second shell, we're going to have a total of 8 electrons. If we put 2 here, we'd have 3, 4, 5, 6, 7, and 8. So if we drew it properly, we could see, oh, we have 2 unpaired electrons, and it wants to share those electrons with somebody else so that they could get a pair. Well, what oxygen actually does is if you had another one sitting here, okay, and it's got 2 on the first shell, then if we draw the second shell, I'm going to start right here, 1, 2, say 3, 4, 5, and 6. What we can see is that if these 2 actually shared with each other, and these 2 were shared with each other, you've got actually 2 pairs of electrons shared between those oxygens. And that is what this picture is showing here, that you've got basically 4 electrons being shared, which is 2 pairs, but it's difficult in that drawing to see how the pairs are really sharing with each other. As they're showing here, this would be the simplified way to draw this. Notice that between the oxygens you have 2 lines, and each one of those lines or dashes is representing 1 pair of shared electrons. So that right there is a double bond. Now it is possible to have triple bonds as well. If you have a triple bond, you're going to have 3 lines between them, and that would indicate 3 pairs of electrons, or 6 total electrons that are being shared. If we look at some other pictures here, oxygen sharing with oxygen makes a double bond. We just looked at that, and that's basically O2, which is oxygen gas. We looked at the bottom one here, D, which is CH4, which is methane. We look at water. Okay, obviously a very common molecule and one that we're going to spend a bit of time talking about. In that case, you've got oxygen. It has its 2 unpaired electrons, and if it took each of those unpaired electrons and shared them with a hydrogen, then you've got a water molecule there. Notice you fill up the outer shell of the oxygen, and you also fill up the outer shell of the hydrogens. So if we go back to our electron configurations, and we have yet another term that we throw in, the atom's valence is a way to describe the bonding capacity. Basically, how many bonds it wants to make. And these are covalent bonds that we're talking about. Okay, so if we look at oxygen, since we just talked about oxygen, oxygen has 2 unpaired electrons. That's what we would call the valence. So it's got 2 unpaired electrons, which basically means that oxygen wants to make 2 bonds. If we look at nitrogen, nitrogen has 3 unpaired electrons. It wants to make 3 bonds. Carbon wants to make 4 bonds. So as we go down the columns of the periodic table, the reason that they behave similar to each other is because they want to make the same number of bonds as each other. Okay, so an atom's valence is the number of unpaired electrons, which will be in the outer shell because the inner shell we filled up before we ever got to the outer shells. And that will tell you how many electrons it wants to make. So if you can predict the number of electrons that you have, and then if you can draw the electron configuration, we should be able to predict the number of covalent bonds that we're actually going to get being made. If we just look at our nitrogen example again, nitrogen, we said we've got 7 total electrons. We've got 5, which we would call valence electrons, and we've got the valence equaling 3, because the valence, again, is just the ones that happen to be unpaired. Notice for carbon, if we look at carbon, carbon has 4 valence electrons. The valence is also equal to 4. So it's possible for the numbers to be the same. It's also possible for them to be different from each other. If we talk about electronegativity, this is a property of individual elements. Electronegativity got kind of a long definition here, but it is the attraction of a particular kind of atom for the electrons of a covalent bond. I like to think of this similar to gravity. So we're fairly familiar with gravity. We understand that that affects the weight that we have. And if we're on the Earth's surface, we do not have the same weight as we would have, say, on the Moon's surface. So we understand that we're heavier here. We're not as heavy if we're on the Moon's surface because it has a different pull on us or a different attraction for us. Electronegativity is very similar. Some atoms are very strong and they pull on the electrons that surround them with a lot of force. Some of them are not so strong. Keep in mind that that nucleus has a positive charge and the electrons have a negative charge, and opposite charges attract. Okay, so the more electronegative, the more strong it is. So the Earth would be like something very electronegative. The Moon would be like something that is not very electronegative. If we look at the periodic table, there is some organization to it with regards to electronegativity. Basically, as we move up the table and as we move across the table, electronegativity tends to increase. So you have this top little corner here where we have very electronegative or very strong atoms located at. In this colored diagram, the very strong ones are shaded in red. Within those very strong ones, if you can see it here, we basically have our nitrogen and oxygen, which are 2 that we said are very common in living matter. Okay, so these are what we would call strong, or you could call them very electronegative. Okay, so they're very electronegative, they're very strong. They're not exactly equal to each other in strength, but they're similar enough for our purposes that we're going to consider them equal, and we want to make sure that we understand that they're very strong. Now, if we look at the other 2 elements that we said are going to be very common, we have carbon and hydrogen. Carbon and hydrogen, notice hydrogen is right here and carbon is going to be right here. They're both yellow, okay, meaning that they're relatively equal to each other as well. If we look at them and compare them to the nitrogen and oxygen, they are going to be a lot weaker than the nitrogen and oxygen. So we want to think of these as being weak, or we could say not very electronegative. So we've got 4 elements that we said we're going to see over and over again. 2 of them are going to be quite strong and equal enough in their strengths for our purposes, and 2 of them are going to be quite weak. We need to make sure that we memorize that our nitrogen and our oxygen are strong and our carbon and our hydrogen are weak. Now, where this becomes important is if they're going to be sharing electrons with each other. If they're sharing electrons with each other and one's very strong and the other one's not, then the strong one is going to be kind of hogging those electrons. It'll be like a little tug of war. Okay, so we classify covalent bonds based on the degree of sharing, or how well we're actually getting sharing taking place between the two partners. Okay, so if we go back to the diagram that we drew before, the hydrogens surrounding the carbon. Now in this case, we've got carbon and it's sharing with hydrogen. We said carbon is weak and hydrogen is weak. So if they're both weak, then they're both pulling on these electrons with the same force. So what this means is that your electrons are going to be shared pretty much right down the middle, okay, for all four of these bonds, because everybody is equal in their strengths. That's what we mean by sharing the electrons equally. Okay, so the atoms have similar electronegativities, i.e. similar strengths, which means they will share equally. Okay, so it's like two equally matched people arm wrestling. Okay, stays pretty much straight up there on the table. So if we look at our example with our oxygen and the bond to another oxygen, this happens to be a double bond here, but one oxygen is going to be just as strong as the other oxygen. So in this case, you've got your electrons basically right down the middle. 4 electrons, but they are right down the middle. These are what we call nonpolar covalent bonds. Okay, so here we have a nonpolar covalent bond in our oxygen gas molecule, and we've got 4 nonpolar covalent bonds when we look at the methane, which is the CH4 over there. Now the flip side of this is when they don't happen to be equal to each other. So if we look at a water molecule, if we just draw it over here, in addition to the picture that you have, in a water molecule you have an oxygen which is sharing separately with 2 different hydrogen atoms. Oxygen is very strong, hydrogen is very weak. So what this means is that although they are sharing the electrons, the oxygen is really pulling on them towards itself. Okay, so they are sharing, but they're not sharing very well. So the oxygen's kind of winning in this. So we're not sharing the electrons down the middle. We're sharing them much more closely to the strong electronegative oxygen. And this is going to be then what we call a polar covalent bond. With a polar covalent bond, the atoms have different electronegativities or different strengths. So this means the electrons are shared unequal, basically not down the middle. Water is a good example of polar covalent bonds. So we've got 2 polar covalent bonds in this case. Now the significance of the polar covalent bonds is that if you are pushing the electrons towards one end of the molecule, towards the oxygen end in this case, those electrons do have a charge to them. They're negatively charged. So not only have we shifted the electrons, but we've also shifted negative charge towards that end. So our negatives are basically going this way. And that's like removing negatives from the hydrogens. So we end up with a molecule that's got little ends that are a little bit positive, which would be the ones that kind of had the electrons somewhat stolen from them, although they are not stolen completely. And then up here we have an end that's got extra negative charge around it, so it's a little bit negative. Okay, so our water molecule is then what we would call a polar molecule. Okay, so a polar molecule, just MC there, polar molecule has 2 distinctly different ends to it. One end that's a little positive, one end that's a little negative. And that is the result of having a polar covalent bond inside of it. Now, if we look at some examples, if I draw a molecule here, so a fairly small molecule here. We've got a lot of different covalent bonds inside that molecule. And we would want to be able to go through and really label whether those are going to be polar covalent bonds or non-polar covalent bonds. The key to this is understanding which ones are strong. That's going to be our nitrogen and our oxygen. And which ones are going to be weak. That will be our carbon and hydrogen. Okay, so if we just run through here, if we look at this bond between the carbon and the hydrogen, Notice that hydrogen is weak and the carbon is listed there as weak. So if you've got a weak one sharing with a weak one, we're going to have those electrons right down the middle, and this would be a non-polar covalent bond. Between this weak carbon and this weak hydrogen, you have exactly the same thing down here, another non-polar covalent bond. If we look between the carbon and a weak nitrogen here, right down the middle, one carbon is just as weak as the other one. If we look at this one between the carbon and the oxygen, notice carbon is weak, we said, but the nitrogen is going to be strong. So if the nitrogen is strong, they're not sharing equally, and that means that your electrons are going to be right down here, closer to the oxygen end. This would then be a polar covalent bond. When we have a polar covalent bond, we have a separation of charges. In other words, that's when we have the areas that have extra negative charges and the areas that are not going to have the negative charges. So they're going to be a little positive. So in this case, this oxygen end is going to be a little negative because it's got extra electrons around it now. In this carbon, we somewhat pulled them away from it, so it's going to be a little bit positive. Between the oxygen and the hydrogen, you've got the same thing. Hydrogen's a little weak. We said oxygen's strong. So we've got our electrons over here, which makes for a polar covalent bond. Even more negative around the oxygen, we've got positive around this hydrogen. These other three bonds that we have, it's all carbons with hydrogens, so these are all going to be nonpolar, or electrons right in the middle for these as well. Okay, notice if you have a nonpolar covalent bond, you're not separating those charges, so we're not putting little plus and minus on there anymore. Even if you have polar covalent bonds, you have little areas that are positively charged and little areas with a negative charge, but the overall molecule is still neutral. And that's because nobody is gaining electrons, nobody's losing electrons, we're just changing the distribution of the electrons. So if we go back and we talk about the nonpolar covalent bonds, examples of these would be between, say, two weak ones. So a carbon with another carbon, or a carbon sharing with a hydrogen with a hydrogen. We could also have two strong ones sharing with each other. So an oxygen with an oxygen, nitrogen with nitrogen, and oxygen with a nitrogen, for example. All of those would be examples of nonpolar covalent bonds, which means it's not going to change where the electrons are located at. They would be right down the middle. If we talk about the polar would be a weak with a strong. So in this case, we're looking at something like a carbon with an oxygen, a carbon with a nitrogen. We could have a hydrogen with an oxygen, a hydrogen with a nitrogen. All of those would be examples of polar covalent bonds because you've got one representative weak one sharing with one strong one. The electrons are going to be shifted towards the strong side, and so you're going to have extra negative around the strong ones, and you're going to have a little bit of positive area around those weak ones in those examples. This picture here, although not drawn right with regards to the electron configurations, it does give you an idea of what we mean by shifting where the negatives versus the positives are at. So notice you've got extra negatives around the oxygen if you were to count it up. If you count it up its protons, it's always going to have 8 protons, so this would be like a plus 8 in the middle, but it's surrounded by negative 10. And then the nucleus of the hydrogen does not have the electrons held as close to it. So that would be where we have our little positive areas at. So that's your water molecule. So water molecules have the negative end, which is around the oxygen, and they've got the positive ends, which are around the hydrogens. Now, it is possible that you have two atoms that are so unequal in their strengths, in their electronegativities, that there is some stealing of electrons that occurs. So in this case, an electron actually moves completely off of one atom and joins to another one. This would not be a covalent bond, because with covalent bonds, we're talking about sharing. Okay, so we're not sharing here, we're actually stealing. If we look here, we have sodium, which is not one that we're going to focus on, but it is very weak, so very weak. And we have chlorine, which is very strong. Okay, so in this case, you've got one that's very weak and one that's very strong. And if they get close enough together, the chlorine basically steals that electron right off. Okay, so it leaves the sodium and it joins the chlorine. When that happens, it took what were neutral over here, neutral atoms, and they become charged atoms over here, because now they do not have the same number of protons as they have electrons. If you go to the periodic table and you look up sodium, sodium has an atomic number of 11, which means that within the nucleus you will always have a plus 11. So here we know for our sodium you've got a plus 11, but if you count up the number of electrons you have here, you actually have a negative 10. So that does give you an overall charge of plus 1. Chlorine is also going to be altered in its charge, and now at this point it has a negative 1 charge. Okay, so we did actually take what were neutral atoms and we converted them to being charged. Now, this is not necessarily a bad thing for these atoms, because if you look at the neutral sodium and the neutral chlorine, neither one of them had a full outer shell, which means they really weren't very stable or happy that way. Once we have the shift in the position of the electron, everybody has a full outer shell. Now, oftentimes students will ask what happened to that third ring on the sodium. Keep in mind that's just a distance. So if we don't have an electron to set at that particular distance, we don't really need to draw the ring on there at all. Okay, so we're not drawing it on. But they both have a full outer shell, so they are very stable. Now, if we have this happen, notice you've got one thing that's got a positive charge, one thing that's got a negative charge, and opposite charges attract. So that's where our next type of bond is going to come into play. If you do have an electron move from one place to another, as we just had, that does create what we call an ion. So an ion is basically a non-neutral atom. So they are charged. They can be positive or negative, okay? But what it boils down to is the fact that they do not have the same number of protons as they have electrons. We can classify these as cations or anions. That really just applies to what kind of charge they have. If they have any kind of a positive charge, we call them a cation. So that could be positive 1 to positive 10 and so on. And if they have a negative charge, then we call them an anion. So any kind of negative charge, we would call them an anion. So an ionic bond is just an attraction between a negatively charged atom and a positively charged atom. So between a cation and an anion. So in our example, we are then going to have an ionic bond form between the sodium and the chlorine that's going to hold them together. Notice that if you already had an atom that had a positive charge and you had one that had a negative charge, those would be attracted to each other right off the bat. We would not have to have an actual scaling of electrons that takes place. Now, just to compare the two, the covalent versus the ionic, notice that with the covalent, you're actually sharing electrons. So this is a physical connection between the two. So they are kind of tied together, stapled together. If you compare this to the ionic bond is just a sticking. Okay, it is an attraction. It is going to be easier to disrupt than what a covalent bond would be, because we're just sticking with the ionic bond like two magnets sticking together, as opposed to, say, stapling or tying two things together. So those are our first two types of bonds. We will see a bit of ionic bonds, but we'll see many, many more covalent bonds this semester. If we talk about some weak chemical bonds, the hydrogen bonds are the first one that we want to discuss. These are going to be very, very common this semester. And these are when you have a hydrogen atom covalently bonded to one electronegative atom that is also attracted to another electronegative atom. So in this example, we can see that we've got this molecule which we call ammonia, and we've got a water up here. And the little dotted line is going to represent our hydrogen bond.